Let's go into details of the most frequently used command of the language, the select statement. This command is used to fetch data from database tables. It may sound simpler than it is, but select can perform line-by-line calculations, filtering, data aggregation, sorting, duplicates deletion, and much more. The query starts with the select keyword, followed by an asterisk if we want to retrieve all columns from a table, or list the names of the columns to retrieve. After enumerating the list of columns, from keyword is used, which specifies one or more tables where data will be retrieved from. To remove duplicate rows from the result, you should use distinct keyword before the list of columns. After the from section, you can specify the where keyword to filter the data by condition. Expressions, including scalar ones, can also be used as columns for selection and filtering. To calculate measures aggregated by columns, you need to specify group by clause and list the columns for aggregation that were used after the select. The having keyword is used to filter aggregated data. Order by is used to apply sorting of the result. By default, rows are sorted in ascending order by the columns specified in order by. If you want to sort rows by descending order, you can use the desk keyword. We've already mentioned that databases can be extended with non-ANCI commands. For instance, in PostgreSQL, you can use the non-standardized limit keyword that will limit the size of the resulting selection to a given number of rows. Let's start with some simple queries. On the left side of the screen, you can see that we're connected to the DVD database, and it contains the following tables. For example, let's see the data stored in the movies table. We want to see data from all columns of the table, therefore we use the asterisk symbol. As a result of the query execution, we see the movie's title, year of release, rating, and etc. Column names are in the window on the left. For example, we want to display only movie names and the release year. As you can see, the result is not sorted. To be sorted the way we need, you should add the column name by which we want the data to be sorted at the end of the order by. All movies are sorted alphabetically now. Similarly, you can sort the data by release year. For example, ascending and now descending. If we need to add sorting by the name of the movie within each year, we will add a title. Now we see that for each year all movies are in alphabetical order. Now if you need to sort by several columns or by an expression, you can use a position number instead of name or entire expression. Title comes first, release year comes second in the select statement. First let's sort by the second column and then by the first column. We see that our result is sorted, primarily by the release year and then by the movie title in ascending order. If you swap the columns in this query, the sort order changes, as well as the order in which the columns are displayed. The release year goes first, the movie name goes second, and they will be sorted by the movie name and only then by the release year. Column names do not always explicitly describe the meaning they have. For instance, it is not always clear where title and release year are referred to without a domain name. Looking at the query result, a person will not know that this is movie data. In order to make the column names more descriptive, we can rename them using the as keyword. New names are just column or expression aliases, and there are no such columns in the table itself. This query-specific column names are changed in the select statement on the fly, sorting the data by the movie name. As you can see, the column names have changed. The first column name is movie title now, and the second one is movie release year. Let's subtract 1000 from release year for fun. We see that the release year of all movies has decreased by 1000, meaning that the expression can act as a column, having the aliases movie release year. Now let's sort by the alias in descending order. There is a movie rating column in the movies table. In order to find out what rating values we have in this table, you need to look through all the values and remove duplicates. In SQL, it can easily be done using distinct keyword, but it is better to use group by. After query execution, we see that there are 5 ratings in our table. We can sort them in descending order. Let's now focus on the actors table and select the actor's ID, first name and last name. First we sort by actor's first name and then by last name. Assuming we need to display the first and last name in one column together separated by a space, this can be done as follows. We will use double pipe to connect strings to each other and add a space character between them, giving the resulting expression an alias, full name. Since we do not have a third column, we will change the sort order, leaving only the second column. Now we see that the first and last names have been combined into one column and separated by a space. Let's try to find an actor with a famous surname. Well, for example, the Cruz. In order to do it, we should apply a filtering condition. You can see that the first and last names on the table start with a capital letter, and since we remember that string literals in the database are case sensitive, we need to follow this rule. Let's run the query and see that there is an entry with such a surname. This data has been artificially modified in order not to keep information about real-life actors. We can convert string literals to uppercase to avoid mistakes in spelling. Let's write down the last name Cruz in capital letters. As you can see, the result has not changed. Now we can find actors whose last name, for example, begins with the first three letters of BAR. We need to use the like keyword and indicate the first three letters followed by a %sign. We have one actress in the resulting set whose surname begins with the BAR letters. What if we want to check several options in one query? In order to do this, the in keyword should be used as a filtering condition, allowing you to specify a set of values. Let's select all the actors with the last name Cruz, Barrymore, and add one more, Hopkins. As a result, we get 5 lines with 3 actors with the surname Hopkins. PostgreSQL allows you to write queries without accessing the table, such as performing any scalar calculations. The expression 2 plus 2 times 2 equals 6. If we add equal to 6 to the expression, the DBMS will check whether 2 plus 2 multiplied by 2 is really equal to 6. This is no longer an arithmetic, but a logical expression. Its result will be either true, or if we change it to 7, we'll get false. Let's take a look at a few helper functions that are useful for writing various expressions. The first is substring, which allows you to extract a substring from a string. In this case, we extract 3 characters from the Leonardo string, starting from the first position, and get Leo. The second one is position, which allows you to find the character position in a string, answering whether one character is contained within another. Let's find the big L in the Leonardo string. The capital L is in the first position. As for the small letter L, we get a 0 result. This character is missing in the string. We remember that L large and L small are different symbols. Now we find the symbol 0. As a result, we get 3, since 0 is in third place. This is the first occurrence of a character in a given word. To compare numbers, you can use the greatest and list functions. For example, the greatest function returns the largest value of those we enumerated. The largest one here is 19.99. If we add null to the argument, it won't be taken into account and we will get 19.99. As for the smallest value, the result will be -24. Let's look at the resulting number data type using pg typeOf function. As a result, we do not have an integer data type, although -24 is an integer. The question is why? We have fixed point real numbers among the arguments, and the DBMS converts all arguments to the same type. And finally, let's have a look at the frequently used coalesce function. It takes several arguments as input, writing null, 10 and 50. It checks values from left to right and returns the first one that is not null. In our case, it is 10. We can add another null and still get 10 as a result. Let's swap 50 and 10. As a result, we got 50. Note that 50 is a string. Now let's check the data type using the pgtypeof function. The data type will return integer. This means that the coalesce function has converted the arguments to the same type. We see that implicit data conversion does not always give the expected result. Therefore, it is better to cast the types explicitly in such cases. For example, if we want the output to be a string, we convert 10 into text. The result will be the text data type. Now, let's go back to the movie W table and see its original language. Let's select the movie name and its language and sort by the movie name. As you can see, the table stores the language identifier, which doesn't tell us much. Language ID is a foreign key to the language table. Let's see the language corresponding to language identifier 1. As a result, we see that it is English. In order to view information about the language and a movie in one query, it is necessary to combine the movies and language tables. We will talk about how to do this in the next module.